All right, we're going to take a minute at the beginning here to review these meanings of these expressions and symbols. Really important. When we're doing these flux problems, we know what all the symbols and notation means. So get a partner. Don't. This is not a formal quiz. This is an informal just review. Okay. So get a partner. Talk through what every single one of these symbols and expression means, and whenever there's an equal sign, write mathematically what it's equal to. Okay, a couple minutes, go. Okay, what is this first thing? RUV. All right, this is the surface written as a vector function, right? A vector function of two parameters, right? Parameterization of the surface. That was the homework you worked on over the weekend. Okay? So super important. So you're rewriting the surface no longer as a multivariable function, but as a vector function. And you need two parameters to write the surface. Okay? All right, what is F? What's that? So we have this surface, right? We have this surface, and we define it as, in terms of parameters, u and v. What is F vector? What is that talking about? The field that this surface is in, right? So we got this surface in space, and there's also, and these are two independent things, right? They're independent. There's a surface, and then there's a vector field in space. And it could be a force field, right? It could be a force field, or it's like a flow field. And so what do we want? We want like the flow rate of that flow field through that surface. So you can think of the surface like a membrane or a net, okay? What is that? S vector. Yeah, this is generically an area vector. Its magnitude is area of the, and the direction of the vector is orthogonal to the elements, right? So this is like a flat element. This is the area, and it gives area and orientation of a flat element. And that could be big or small, just as long as it's flat, right? The magnitude of that vector is the area, and the direction of that vector is orthogonal to the plane of that element. So then what's S? What's S? Yeah, just the magnitude of that vector, right? So it's, what is it? Area, right? So that's just the area of your flat element. So then what is ds vector? What's the ds vector? Okay, so you're talking about how to calculate it. All right, I'll write that down. So it's RU cross RV which is what you get when you cross this vector with this vector. So where have I drawn the ds vector in this picture? Do you see what the ds vector is? It's this one here, right? Its magnitude is what? What is its magnitude? What's that? What is the magnitude of the ds vector? Represent, or what is it equal to? It's still an area vector. It's still an area vector. But what's the difference? Yeah, so it's when we're gonna cut up our surface, right? We're gonna cut up our surface into lots of little elements, and we've gotta approximate all those little elements, and they can't be curved, right? So we approximate them with little flat parallelograms, which I'm drawing in red here. Okay? So this ds vector, its magnitude is what? the easiest question. Area, right? The magnitude of an area vector is area. The magnitude of an area vector is area. This is just a tiny one, right? This is just a little element that's trying to replicate like a little curved patch in our surface. See, the reason we're doing this is because the force field can vary, and so we need to get it small enough so we can consider the vector constant for a little patch. Does that make sense? Sound familiar? This is integration, right? So we're going to just make things small enough so we can consider for this little element, this little parallelogram element, the force is constant through that. We're just going to pick the one force for that. And then, so that vector ds, then its magnitude is the area, and its direction is what? Orthogonal to the parallelogram, right? And that's exactly what cross product does. Cross product, its magnitude gives area, and its direction is orthogonal to the plane of the two original vectors. It's perfect, right? It's exactly what we need to do. So then what's ds? Right, it's just the area, right? So it's going to be, oh wait, so this is not right. This is what this is. Sorry, got that wrong. So this should be this. It's truly the vector, not the magnitude. So the magnitude is what I wrote before. That's ds, so that's this. The magnitude of that vector. What was n? What was n? The unit vector in the direction of? There, yeah, ds vector, right? So it's the unit vector in this direction, right? So if we unitize that thing, we get it's all this divided by the magnitude of that. Okay, and then what's the flux? Integral over the whole surface S of F dot ds. Okay? So we could rewrite that ds as the unit vector. Isn't this ds the same as the direction times its magnitude? Right? This is the direction of that as a unit vector, and that's its magnitude. So can't we always also write it like this? Isn't that fair? Can we do that? Because n vector ds magnitude is the same as ds vector, right? Because n, that's the unit vector in the direction. Okay? And then we saw that that is equal to F dot RU cross RV du dv. And now this thing projected into the plane of u and v we'll call, say, r. So this actually gives us an alternate. So when things are simple, this is a faster way to set up a flux integral rather than having to parameterize and find the cross product. And we'll see. I'll show an example of that. Okay. So this form, under the right circumstances, gets us a streamlined setup that can avoid having to do a cross product. Okay. So we'll see an example of that. Okay. Questions on this review? So super important that you're keeping track of what the symbols mean as we're putting things together here. Are we good? Yes, please.
How does the direction of the vector S compare to
This one?
Yes.
So this is, um, this was just like when we started, before we did any of we just talked about what an area vector was. So it's always perpendicular to the surface. So we were normally talking about, so for some like flat surface, the S is just perpendicular to that surface and has the magnitude of the area of that surface. I don't know, does that answer your question? So then this generically, so it could be the area of this, but then we also use S just to represent like the whole curved surface that we're talking about. It's kind of like, and that's how I'm using it here. S is just like, what is the surface in R3 that we were finding the flux through. Does that answer it? Okay. Yes, please.
So for the flux, we're moving from S to R. R is the 2D projection into a plane, right?
UV, yeah.
Okay.
Except that sometimes there is no there is no UV plane we can imagine, but we just kind of like if it's phi and theta, like if we're U and V are spherical coordinates, we're doing phi and theta. We don't have a phi theta plane necessarily, but it's still the same idea that it's like the corresponding projection. It's the projection of that into this coordinate system U and V. Yeah. So this is like when we're getting ready to solve it as a double integral, as a standard double integral. Other questions? Okay, so we're finished. Let's finish up the example from last time. This flux example. Okay, we made it this far on this. So we were finding the flux through the part of this paraboloid that lied above the unit square. Okay, so we were finding the part of the flux through the paraboloid above the unit square, and we were just at the point where we were saying, so we could do some kind of polar parameterization or an XY parameterization, and we decided we should do what? Remember? We decided XY, and what was the reason? Yeah, because when we get to integrating, then X and Y are very simple in rectangular coordinates, 0 to 1, 0 to 1 for X and Y, since it's the unit square. So we're going to have X, Y, and 4 minus X squared minus Y squared is the easiest type of parameterization, when you can just have X and Y be your parameters, and then Z is just your function of X and Y. So then what do we have to do? We're going to do Rx, find the cross product of Rx, Ry. So we do I, J, K, partial of R with respect to X, partial of R with respect to Y. What's the partial of R with respect to X? 1, 0, negative 2x. Partial of R with respect to Y, 0, 1, minus 2y. Okay, so then Rx, Ry is cross product. It's going to be, so I 0 is at 2x. And then J is going to be 0, 2y. And K is going to be 1. Okay? Am I good? So now we're ready to set it up. It's going to be the double integral of f. And now we're doing it in x and y, so any z's then, we're going to replace the z's with this expression right here, because this is what z equals on our surface, right? Z equals that on our surface. So we'll have xy, this is f, we're doing f dot ds, right? So xy, y times z, 4 minus x squared minus y squared. And then zx, 4 minus x squared minus y squared x dot what? This is our rx, ry, right? So this thing right here, 2x, 2y, 1, dy dx. And so y goes from 0 to 1, x goes from 0 to 1. So we just do the dot product. So this is long and tedious, but not hard, right? Just a lot of polynomial terms, right? Polynomial terms, easy to integrate, just would take a while. So right, so like this S here, this S is this whole curved patch that we're talking about, and then the R would be what? The projection of the xy plane. That's what we're integrating over, right? So that's that difference between the S and the R. Questions on this? And what does this find? This finds the flux, the flow rate of this field through that little part of the paraboloid. Questions before we get to harder one? That's going to have an easy one. Any questions? We good? Can I erase? Okay. All right, so if you notice, so when we had x and y, we did that cross product. It's kind of going to be the same every time you do that. So every time that you have your parameters are x and y, and you write it this way, like we did in the last example, you're kind of going to be doing the same thing every time. So let's find a general form for that, so that we can just, whenever we parameterize an x and y, we don't have to go through that whole procedure of the cross product, because we're going to get the same thing every time, right? So here we go. I'm going to do it fast for time's sake. So Rx is 1, 0, and partial of g with respect to x, right? Y is 0, 1, partial of g with respect to y. So my Rx cross Ry is going to be 0, what? Negative the partial of g with respect to x, and then negative g with respect to y, and 1. So whenever you parameterize in terms of x and y, your cross product will always be this. But we can keep going, right? So we can keep going over R. So what's F then? F is going to be my P, Q, R. That's the field now. That's the field. Those are the components of the field. And then we're going to do dot, the cross product, and then dA, which is our dx, dy. So doing the dot product, we get the special, this is like a special case form. We get minus P times the partial of g with respect to x, minus Q times the partial of g with respect to y, plus R, dA. So whenever you're parameterizing your surface in terms of x and y, you can just jump right to this as the flux and bypass all that stuff, because it'll be that same stuff every time. That cross product will be the same. So whenever R is an x and y, and your surface is the multivariable function g. So this is what? The flux when you've parameterized your surface in terms of x and y. You can just jump right to that, and it saves a lot of work and time. Questions on that? erase. Everyone good? All right, so let's do a longer example. So I want to find the flux through S, and this is a closed surface now. Remember, a closed surface has an inside and an outside. I want the part of the unit cube below y plus z equals 1 in this field with inward orientation. Okay, with inward orientation. So let's sketch what we got here. So the unit cube is? It's a cube of side length 1 that lives in the first octant. But then we want just the part of that cube below y plus z equals 1. What's that mean? So what's y plus z equals 1? How does that relate to that cube? Yeah.
It's a plane that cuts it in half diagonally.
Right, because this is, so y plus, so if you think about, this is the line, y plus z equals 1 is this line, right? And so the plane then just extend in the x direction. And so we're going to have that. It's going to be like, it's going to be below that. The part of the unit cube below that plane is going to be like the bottom wedge, right? So all this is gone. Okay, so how are we going to find the flux through this closed surface? What will that look like? Finding the flux through this closed surface. What will that consist of? I need to find the flux through this closed surface. Yeah, Jacob.
Would you add the flux going in and subtract the flux going out?
Okay. So how do we know where it goes in and where it goes out? Yeah. So yeah, when we do that, that will kind of happen naturally, right? So wherever there's flow going in, we'll get a positive contribution. Wherever flow is going out of this thing, we'll have a negative contribution. So that will work itself out. But what's our strategy for doing this? Yeah.
Would you integrate for each side if such a new flux?
Yeah. So we got what? 1, 2. We got 5 different flat sides. So we got to do a flux integral for each one of those. Okay. 5 times the practice, right? So let's label our surfaces here. Say S1 is the bottom. And we'll do S2 as the left side. And S3 will be the front. And then S4 will be the back. And then the slanted plane of the top will be S5. So here's where we can make good use of that, what I said, that alternate form, right? We said that F dot ds is equal to F dot N times just the magnitude of the area. Those are the same. So we can use this when we're going to use rectangular coordinates. So I'm going to use this. Use into the conditions of rectangular coordinates for a plane parallel to us, plane parallel to coordinate plane. So which ones of these apply here? So if we're going to use rectangular coordinates and the surface is a plane parallel to the coordinate plane, then which of these pieces of our closed surface apply? S1, S2, S3, S4, S5. All of them but S5, right? So S1 through S4 meet this criteria, and so we'll have a lot faster track setting up these flux integrals rather than having to do cross product stuff, okay? So S1 is the bottom. How are we going to parameterize that? So we're going to parameterize, so we'll call that R1. What variables should we use to parameterize S1? Bottom surface. So what two variables will help us get all the points on that bottom? X and Y. And what will the parameterization be? He wants X, Y, 0. Agree? Yep. Let X be X, let Y be Y. All the Z coordinates are 0 on that. And then what is our N for that? So say N1. The unit vector, and we want inward orientation, right? Inward orientation. So we want the unit vector orthogonal to that plane so that it points inward into the closed surface. So what would that be? You want 0, 0, 1. Agree with that? Good. All right, so why don't you do, I'll start taking some attendance here. Why don't you do that? No, let's just do this fast for time's sake. Let's just keep going. So R2. R2 is the left side. What variables are we going to use for that? What is it? X and Z. And our parameterization of that plane over there will be X, 0, Z. Y is always 0 over there, right? N is inward orientation. 0, 1, 0. Pointing in, right? Pointing into to the interior. All right, the front, S3. R3. What variables do we have? X and Y? Y and Z. All points on that plane can be described as 0, Y, Z. Is that right? 1, right? So all the X coordinates are 1 on that plane. So it's going to be 1, Y, Z. Inward orientation. N vector will be? So it's going to be negative. We go negative because of the inward orientation. So the inward orientation takes us in the negative X direction. Okay?
So why is it not negative 1/2 that's just the direction?
You good? Yeah, that's just the direction orthogonal. Okay, so R4. What is that? The back. Parameters. Y and Z again. All points on that back surface can be written as 0, Y, Z. Good. And 4. Inward orientation. positive 1, 0, 0, right? Ask if I lost you somewhere. Okay, so now the top we're gonna go back and use this, but when we do the top, how are we gonna parameterize the top? R5. What should we pick for our variables? Yeah, make it as easy as you can. Whenever you can use XY, use XY. And when we do XY, we're gonna get X, Y, and 1 minus Y. Because all Z values are 1 minus Y on that plane. Here, we can use our, special case that we just derived. Remember that? Where our, the negative GXP, negative GYR. So when we set up that, we'll do that. Okay, so now I think, let's do attendance. And you guys start setting up and solving these integrals. So the first 4 should be quick and easy because we're going right to this, right? We go right to this. So all you have to do is f dot n, and it turns out because you're in a rectangular coordinates parallel to the coordinate plane, ds and dA are the same thing. So in that case, then ds equals dA. And so those first 4 should be really fast. And then in the 5th one, you're setting up that you're doing the special case. That thing we derived when you're parameterizing in x and y. Okay, so check with each other as you go. And our goal is to get the total flux inward into this surface. And I'll take attendance. Okay, for S1, did you get 0? Any questions on that? It's I'll just say it verbally. XY y squared 0 dot 0, 0, 1. Is that what you got for S1? XY y squared 0 dot 0, 0, 1. Turns out to be 0. Yes? S2. You should get 0 because it is 0, 0, z dot 0, 1, 0. Is that what you got? 0, 0, z dot 0, 1, 0. How many people got that? Do I need to write out one of those two? S1 or S2? S3. For S3, I think this is non-zero? Let's write that one out. So for S3, you get integral so xy y squared z. xy is y squared is y squared, z is z. That's your function. That's f on that surface, right? So you use the parameterization of the surface to rewrite f dot n. What's our n? Negative 1, 0, 0. And that's going to be, say, dz dy. So that's S3. That's the front. So we get what? Negative y, dz dy. And then if we do, well, let's do dy dz. Let's do type 1, make it easier, right? No, dz dy is type 1, right? dz dy is type 1. That's what we want. Type 1, dz dy. Z goes from 0 to 1 minus y. And y goes from 0 to 1. All right, let's just make sure. Are we all on the same page for setting up the double integral for 3? I got the integral of negative y dz dy as z goes from 0 to 1 minus y, and y goes from 0 to 1. Camille likes it. Jacob likes it. And what does that equal? Anyone got a value for that? What is it? Is that negative a sixth? Is that what that is? Okay, ask. That's what you got? Cool. If I lost you, ask. It's okay to ask. S4. Is another one that's 0. For S4, you get 0 y squared z dot 1 0 0. And that turns out to be, that's just 0. So my f dot n is, for 4, 0. So I'm looking at S4, 0 y z. So xy will be 0. Y squared will be y squared. And z will be z. But my n vector is, for 4, 1 0 0. So that's the integral of 0. So it's going to be 0. Okay, S5. This is actually kind of the more interesting one here. So for S5, we're going to use our special case form, right? So it's going to be negative. We know it's going to be in terms of x and y. So negative p, which is xy, times the partial of, and what's the function we're doing? So z is y minus 1, or 1 minus y. Is that the red function up there? So p times the partial of g with respect to x, which is 0, minus q, y squared, times the partial of g with respect to y, which is negative 1, plus r, which is z, which is 1 minus y. So that's our minus p partial g with respect to x, minus q partial g with respect to y, plus r. Using the special case when we're parameterized in x and y. And then that's just going to be what's our r we're integrating over. dy dx. Isn't that just the unit square? 0 to 1, 0 to 1. So S5 is, I get negative 5/6. So I times 0. Yeah, so if you do the math, you should get negative 5/6 for S5. Therefore, did anyone get through all that yet? It's okay if you didn't. I just thought maybe. But that's what you'll get. When you do that double integral, which is not hard, but we'll just won't take the time to do it, you should get negative 5/6. And so therefore the flux inward through S is negative 1. You're going to add them all up, right? So we're just going to add up all the net flux through all the 5 sides. And we only have 2 non-zero. We got the negative 1/6 from side 3, which was what? The front. And then the negative 5/6 through the slanted top, so negative 1. So what does that mean about the net flow through this surface? Yeah.
Yeah, same.
Positive 5/6.
Yeah.
Ruh-roh. Let's see. Negative. Oh. Did I? Hmm. Okay, well, we're gonna do this a different way in a couple days, so we'll just make a note of that. I'll just trust you guys. So it's either -1 or positive 2/3. If it were -1, what would it mean about the flux? What would it mean about the flow for the surface?
It would mean that there's an outward flow of one.
Yeah, the net flow through that whole thing would be outward with a magnitude of 1 because we oriented inward and got a negative value. Okay? And then if it were 2/3, if it's 2/3, according to you guys, it's 2/3. According to me last semester, it's -1. So if it's 2/3, what would that mean for the flux or the flow? Net flow inward of a magnitude of 2/3.
I have a question on that.
Please.
I may just be missing something. But
Yeah.
How is the first one x squared?
S4.
The S1.
S1.
Yeah. On the actual x
So
x squared, y squared, 0, 0, 0, 1. How did you get x squared?
I'm still not aware.
You didn't write it up on the board.
Okay, S1. I said it out loud. So S1. I said that F would be xy, y squared 0. So that's what F is. Xy, y squared 0.
You said x squared.
I might have, but I meant to say xy. Yeah. So I meant to say xy, y squared 0. Dot. But it doesn't matter. It doesn't matter what that would be because it's dot 0, 0, 1, so it just goes away. But yes, I should have said, if I didn't, xy, y squared 0. Does that answer it? Other questions? Okay, so for Monday night, you have the next two webworks, which are both about this stuff, Flux. I'm going to post a video of the next example, which will be helpful for doing those. So what I did last semester on this next example that I was about to do, I'll post that so you can have access to that as you're working on the homework for Monday night. And then there's, I think I posted some written work too for Monday. But make sure you come to, so great attendance today. Thank you all for coming. Make sure you're at every class next week. This is the hard stuff, and you're going to feel like you miss a lot if you miss class. Happy Thanksgiving. Gobble, gobble. Okay, here's where we left off in class, and Tingyu came up after class and was able to point out what happened here with the negative 5,6 versus the positive 5,6. So when we did S5, we found the flux through the top, and we used the special case. Well, the special case would be for a positive Z orientation. So this number that you guys got, this positive 5,6, where that's correct for this, now if we're talking about what's the inward orientation, the contribution to inward orientation of the flux of that top face, it'll be negative 5/6 because the positive 5/6 would be for upward orientation for Z, the positive direction for Z. So truly for inward orientation, we want to use negative 5/6, and then the flux inward is -1. So you were right that the value of the integral is 5/6, but that special case is for upward Z orientation. So for inward orientation of the whole surface, we need to make it negative 5/6, and then the net flux will be the -1. Okay, hope that clears it up.